Weekly or bi-weekly libembeddedhal meeting. It is June 1st, 2022. All right, so here are some of the highlights. First, I'm going to go over the progress report, kind of see how we did for iterations 3 and 4. We did skip last bi-weekly meeting, so we have quite a bit of time between these two, so I'll go over what's been changed with that. Device simulations for testing, serial communication. We've kind of, me and Davi talked about this along with other people on like how we should go about doing serial communication, and we kind of came to a conclusion. The introduction of high bandwidth interfaces. We haven't written any yet, but we do plan on adding them in the future. Another couple of interfaces such as rotator and aligner. And then I want to show you guys the updated and thorough documentation. And then finally, removing global uptime. And I think actually the order is slightly off. Updating the documentation is actually the first thing we'll be talking about. Well, progress report, then updated documentation, then everything else. So actually, before we move on, let's take a look at the progress report. So it should be 2 iterations ago. So here's our current, and here are the last 2. So iteration 3, mock SPI, mock serial, and mock I2C were all basically closed as won't fix. Just because of the fact that if you hadn't seen that message before, this has to do with the fact that there was some one-size-fits-all options that could work for quite a few of them, but it made more sense to have the ability to create an entire fake that represents that object and design the basically fake that thing as it is versus trying to develop some type of generic solution that works for a part of things and makes your life harder for like it can make some people's lives easier and some people's lives even harder when they're trying to force that mock into their use case. So eliminating those things was the idea. We might make utilities for it. I'll talk about that later. So I got some libx bit set stuff set. Milo got a stub for ADC put in. And I came up with the serial communication, how we should handle it, and that's where one of the slides is. Mock ADC. I'll put that one in. I got the basic usage of libembeddedhal and the README, but the majority of this was actually just eliminating the stub, the concept for the stub. We have a message about that from a couple layers up. So if you want to check that out, you can. And that's pretty much it for the progress report. So not much was actually done. Yeah, a lot of things got closed out, but like there wasn't as much stuff that should have been done. But not to worry, we actually moved the iterations out by 1. The due date is now. The early launch date is now September 6th, and then the final launch date is now October 18th. Okay. Oh, and remember, if you have any questions or comments about this as I'm talking about it, feel free to just unmute and talk. Okay, and let's get back into it. So, first things first, updated and thorough documentation, or at least more thorough documentation. It still has parts that are empty that need to be filled out. I have bugs for those. Let's take a little look. Yeah, so this is actually, I made sure to go to the exact commit so that if anyone ever looked at the old slides, they could see exactly what I was talking about when I got here. I'm just gonna go over to code here. We'll see the README here, typical stuff on here, a little bit of reorganization of where things are and like the links here. I actually just realized right now that I still need to add in the fact that we depend on Conan and how to install, or at least links to where to install it. Here we have the overview information. So like, I think this is really important. It's kind of like our mission statement. Just so everyone understands what we're kind of focusing on is libembeddedhal exists to make hardware drivers portable, flexible, accessible, and easy to use. Really kind of honing in on the hardware abstraction layer, the how portion of this. And to make sure we make choices that enable this, because this is what we honestly need in order to make a future that provides or makes it a future where firmware code can be portable, where you can take your firmware code from one application to another and your thing work without having to do a lot of other work for it to happen, without having to like rewrite everything yourself. So we have a couple of project attributes. There's some changes here. You can take a look at that if you want. A glossary. I actually highly recommend everyone kind of look through this so they understand what terminology we're using for things. When I say words like target, when I say words like interface, when I say things like peripheral drivers and a device driver, these are different things as we label them. soft drivers, hard drivers, which are just basically peripherals and device drivers, off interface functions, this kind of thing. Also have demos, a couple examples. These should actually just work. Yeah, these should all just work. Same thing with a blink. These should all work here. Library structure. So if you hadn't already really kind of figured it out by now, you can kind of see it here. It's pretty simple and short, so you can kind of read this, but it's another thing to look at. How to use utility functions, what they're meant to do, using device drivers. This is all like, users who want to use things, not really telling you about how to develop things. But by knowing how they're supposed to be how they're meant to be used, you can also figure out or be better at developing them yourself. Soft drivers and what they're supposed to do, and utility classes still need to update percent, frequency, how to use MPU units. There's a little section here for handling errors. Sorry, it's a very large section. Handling errors is, I don't think, usually ever that simple, especially when you want to have a reasonable or kind of well put together example, especially when you're documenting everything in comments. Customization, some techniques, the ones that are actually going to make libembeddedhal useful and powerful. This was my technique that I came up with before the CPP cast. Trying to figure out a way to originally to explain how virtual function calls or what I'm looking for. Indirect function calls can be as fast. Way to take interfaces that are runtime polymorphic that use the keyword virtual and give them the same performance or the opportunity to have the same performance as static polymorphism. If you don't understand what that means, there's some description here that kind of explains what's happening. I think it would actually be good for me to put in a little demo here, so people can go to Godbolt and check it out. I have one that's available. And then also how to support multiple platforms. And some other extra things here like library badges and that kind of thing. Highly recommend you guys take a look at this. It's really good for if you're developing stuff for libembeddedhal to understand all the stuff that we use and how things are supposed to be meant to be used, that kind of thing. So yeah, that's the new thorough documentation. I recommend that you guys take a look at it. There's a lot of good information in there, and may also answer some questions about things that I've said in the past that you may have just kind of glanced. Oh, okay, I'll probably learn that when I need it. This might actually give you that information now. All right, so on to the next section.
Let me stop you there. Can we make edits to that documentation?
Of course you can.
Okay, perfect. Thanks.
You seen some typos?
Well, I probably as I read through it, I'm expecting to see typos. Yeah.
Oh yeah. Just go. Yeah, you can absolutely just update things.
All right, perfect. Thanks.
Yep. All right, so another little section here: device drivers for testing serial communication. So yeah, closed out mock I2C, mock serial, mock SPI. There are some really good ideas that I've and other people have had on how to mock these separate things individually. I think we might want to come up with names that don't scream like you should use this thing for developing your stuff. Like for example, using an unordered map with a single byte as the key and a single byte as the value in order to map addresses to actual byte values. That can work very well. So you can do something like that. But if you also want to not like move outside of that, you can also do it yourself. So the whole point here is that these communication protocol, fakes or mocks, stuff like that, we're removing those. Now we're actually just going to make demos. We're actually going to write a library for MP650, ESP8266, and this last one is the controller for a OLED display. And rather than just like writing the mocks, we'll write examples that make their own fakes, make their own simulated device, and people can test using that. So rather than a one size fits all, we have a many sizes to fit most things approach. We're going to be going with a custom fake for each driver. So try not to fit all or even some of the things. Just let people design it as they see fit, because most devices are very different from each other. And if they are that different, then it doesn't make sense to try to squeeze them into one area. It just makes the tests more complicated and more confusing. And finally, when patterns are found, we can make utilities make those faking devices easier. So we'll wait until we see the patterns, and when we start seeing the patterns, we will start making utilities for that. Any questions on this?
Are these changed respectively?
Say again?
Are these replaced respectively?
Actually, yes, it is. Yeah, MPU to I2C. ESP8266 for serial, and SSD 1306 for SPI.
What's the approach idea when it went from one size fits all to many sizes to fit most?
Yeah, so we were considering different types of. We were looking, like me and Davi were actually looking through a whole variety of different devices for SPI, I2C. We were kind of ignoring serial because it's a almost always it's every device has its own protocol. So it's really hard to figure out a common pattern for that we could then make a mock for. And we found some really just awful, really weird implementation I2C communication protocols, or usages of I2C and SPI. So at some point we're like, we could try our best to make some things, some of a memory map type thing, but in the end, um, it doesn't really fit. And for SPI, it fit very few things actually. And for I2C, it fit a lot of things, but then it got real complex really quick. And then you have to think about it ends up getting you stuck into this little loop of you get stuck because you're like, okay, this is the right thing to use, the right tool to use as what I expect. But then when you try to do things like, oh, I need this particular section of memory to update, that gets more convoluted. That gets a lot harder to test for. So it's actually probably better in our better interest to design unique fake implementations or fake representations of these devices in a way, a simulation of that device that you can kind of control, or that you should be able to control, and use those for tests versus a more generic way.
Which one would you say we're catering more towards?
What do you mean?
You kind of gave the example of, um, forgive me, I don't remember a lot of this terminology, SPIs versus, was it I2Cs? You said that one fit kind of some, but the other.
Oh yeah, so I2C is way more prone to having protocols that are memory addressed, and then SPI is very common to have a command, send out a command with maybe some parameters and get a response. That's very common for SPI, but then you can see the reverse on either side. So it's a toss up, and you can develop for both of those, but then you find people with really odd ways of doing either one. So you end up making these absurdly complex mocks.
Gotcha.
Yeah.
I see.
So and then at that point, like it just becomes harder for people who are doing their own tests to actually test things. Where if you just tell them, well, you understand this device, you understand how it's supposed to work, you should be able to write a fake representation of it, and anyone who wants to know more about how that particular device is going to operate can look at that. Well, the documentation normally, the data sheet, and then you can also look at the actual fake itself.
So we're not catering to either one. We're asking the user to make a mock representation of what they want in order to use this.
Yep.
Okay.
The user, in effect, is somewhat developing a simulation of these hardware devices in order to test against them in their software. So yeah, good questions. All right, next up, high bandwidth interfaces. Check my time. Cool. Yeah, so high bandwidth interfaces are versions of interfaces that support high bandwidth communication via spans in the interface. What that kind of means is that in general, if you have an interface that just takes like a couple variables or a couple bits of data, you just get those bits of data. If you bring in a span, it's basically saying you're bringing in an array and a size, so you can fill up an entire array worth of data. I2C, SPI, and serial are already high bandwidth interfaces because they all deal with spans of data. They never really deal with individual bytes. That was an idea really early on, which was to have I2C and SPI operate, well, I2C almost never, but SPI in single bytes, and serial with single bytes. But that just results in a whole slew of problems. So there is really no low bandwidth version of those three communication protocols or those particular interfaces. But as an example of something that we currently have that exists that only has a low bandwidth version is the ADC interface. You grab one sample at a time, and that's how the interface works. We may probably going to make a high bandwidth version of this as well in the future. This is mostly meant for sensors like compasses. Well, compasses are actually really low frequency, but accelerometers are really high frequency, so gyroscopes. I can imagine there'd be a faster frequency compass, and I can also imagine like other ADCs for like sampling really high bandwidth stuff for whatever application could also use and would want a high bandwidth interface. The pros, faster data transfer. The cons, tends to be more complex and thus increases binary size. The resolutions to have a interface for both high and low speed come from the two realizations that the interface that we're thinking of, trying to have like, oh, well, how do we figure out how to make accelerometer work for low and high speeds, broke two problems. Broke two principles. I from the solid principles, which is interface segregation principle. That basically just means that like um, it's better to have a set of multiple interfaces versus having one interface that does multiple things. Um, yeah. Case in point, if you have an accelerometer class that has or interface that has a single sample interface and then also a multi-sample interface, I could imagine is there's any weirdness trying to handle either one, but that's I have an example coming in the next one. The second part here is that it breaks zero overhead principle, and I'll go into what that means and how it actually broke this in the next slide. The situation. So let's say we have an interface like the one below. Here's our span. We take in a whole set of data. But if you just want to grab a single sample, it's about a lot of boilerplate. You have to make an array, you have to pass the array in, then you have to look at the first value of the array afterwards. Yeah, at least 3 lines you have to deal with when it comes to this versus ADC or like accelerometer as it is now. You just grab a single value at the return type at the return, and you're good to go. It's a one-liner. You could also write some utilities to make this a one-liner, but I'll explain to you why that's not a good idea in a sec. So this interface implies that the driver sets up the device for large data transfers. So because we have this interface, it would make sense for us to write the documentation for it that it needs to be able to support, like you should be able to give it like 1 kilobyte or like 1,000 samples, and it would go and stream out 1,000 samples up to the point where it runs out of its own data. If you're going to do that, then that means you're setting up FIFOs in some MCU. You're configuring some clock rates to get the sample rate just right. You might be configuring some of the pins to act as interrupts, that kind of thing. So there's extra work that needs to be done. And the next little bullet points is that just there. A low bandwidth application, you have to pay for the additional. Sorry, actually, I meant to say for high bandwidth application. Or I'm sorry, if you're using it for low bandwidth applications, you have to pay the additional driver setup. So that means setting up clocks, rates, everything else like that. And you also need probably another thing like an interrupt pin to drain the FIFO to get the data out of the device. A lot of things need to be supported. And in this situation, you deal with this problem. You paid for more than what you're going to use, which basically breaks the zero overhead principle. And you paid for a setup you didn't need. And that's a cost that like you didn't have to pay if you just chosen the low bandwidth solution. The other item here is that you make either implementation as small as possible if you separate them up. You only have to write the smallest amount of code to get a single sample read out of an accelerometer if you just have a low bandwidth version. If you have a high bandwidth version, you kind of know what you're coming into. You know what you're going to expect. Possibly DMA, interrupts being fired, that kind of thing happening. So it's a way to separate the responsibilities so that you can choose either one for your application versus having a one-size-fits-all and then having kind of the worst of both worlds. So yeah, that's kind of the high bandwidth interfaces. Any questions on that? If you're wondering where this came from, Davi works on sensors, high acquisition systems, and needs an interface that would be able to get accelerometers running at like I forget how fast, like maybe like 100 hertz, which is a lot of data to pull. So having the return type just be acceleration each time doesn't really fit. So yeah, we haven't developed this yet, so this is something that's gonna happen soon. But like this is something that we are planning on including. All right, next slide. All right, so this is short. 2 other additional ideas that came from Matt. Basically, things that you'll see around when it comes to the servo area is rotators and aligners. A rotator is a closed-loop rotary actuator, basically a motor, but with angular velocity control. And this little cool idea is that you can actually use a soft driver to downcast that to an embed motor. Why would you ever want to downcast to an embed motor? For reminders, the normal motor, embed motor, is open loop. So you kind of tell it how much power you want to apply, but you don't actually tell it what velocity you want it to run at because it doesn't have feedback to do that. That just would be useful for particular applications that need an embed motor, but all you have is a rotator. So it's a way to kind of make that conversion. We also have embed aligner, a closed loop rotary actuator that has continuous and positional movement. Also can be downcast into motor, rotator, and servo because it has all those capabilities. Um, this may seem like it's doing too many things, but I think that this particular interface basically forces the like if a driver asks for an aligner, it's asking for something that has all these capabilities built in, and this is very much a possibility. The motors that the robotics team at SJSU use, the RMD X6 motors, those are aligners. They have both continuous motion and also positional rotary motion. Any questions about these? Cool. All right, and this is, I think, the last one. Yes. So removing global uptime and sleep functions. Let's see, what time is that? 7:23. 7:22. So yeah, so removing global uptime and sleep functions, and focusing on making libembedded HAL as non-intrusive as possible as a HAL. So as a hardware abstraction layer, the global uptime sleep functions will be removed. There's no reason to really keep some type of global state. We should be doing nothing but just being drivers that work on their own, do their own thing. We can have global data for a driver. That's fine. Like for example, the interrupt vector table needs to have some data laid out somewhere statically. It can be heap allocated, but it needs to be laid out somewhere in which it to reassign the IVT's location. So you need to have that data somewhere. But this is not necessary. The definitions for sleep and uptime will be kept, but you may be wondering, why are we doing this? Well, the removal means that each driver will have to accept a sleep or uptime function in their constructors if they need that information. This allows the application developer the opportunity to provide a separate uptime and sleep function to separate drivers if it sees it as useful. So I don't know, maybe I've decided that for my sleep counter, I'm going to use vtask sleep from FreeRTOS and provide that sleeper to one function. I have another function where I know that the sleep function cannot be vtask sleep because vtask sleep, or vtask delay, I meant to say. Ooh, it's been a while since I've done FreeRTOS directly. That, in that particular case, for another driver, may need to look at the DWT timer, which is a lot faster. It's at the speed of the CPU's clock. So if you know what the application needs, or if the application says, hey, or like that particular driver says, hey, it would be in your best interest to use a high-speed sleep function that just delays you versus actually sleeping for an entire millisecond, otherwise timing would be distorted, then you can make that kind of choice. You get this flexibility. What this basically does for us is that it improves flexibility for hard drivers with a small, actually even soft drivers, I probably should have said drivers in general, with a small cost to object size. You need to be able to store that uptime or sleep function. If using std function to make it polymorphic, that'll be about 32 bytes. I think it's like 16 bytes on ARM for 32-bit CPUs. And then for, if you just do it directly, you don't do std function and you actually take in a template for a function object, like a functor or a lambda, then you pay maybe a pointer. Well, lambdas will be whatever size lambda is, but for the functor or something like that, it's usually just gonna be a pointer. Becomes a dependency injection site for testing. So you can actually know, you can actually test that, the time delays that you applied were actually being applied by the code. You can sum them up to say, hey, the total amount of duration of time had to have been around about this, and be able to see that. And then removes code smell of thread unsafe global state. So like being able to change the uptime and sleep functions, it was always unsafe, and I was considering ideas of how to make it thread safe. Maybe have some sort of, make it templated and then let the person put in their own lock for it. But then you then take that template and then I don't know. I was trying to come up with a way with this, and then I also realized that you just didn't, after I decided I was going to remove this, I was thinking about what other problems we have here? It's well, it's thread unsafe. And I started thinking about if I was going to make it thread safe, what would I need to do to make that happen? And it got a little bit more complex than I wanted it to be. It made me realize this is still not useful. Oh, and the main rationale, I didn't really explain that here. The main rationale for all of this is that I don't want drivers to just use the global uptime and sleep functions all the time, because if you ever wanted to have that flexibility back, you either change the driver yourself, rewrite it, copy it, and change it yourself, or you ask the vendor the maintainer of that library to update it to allow for your own timing or uptime sleep functions. Or you have to, and this is the complex part, if you don't want to touch any of their code, which makes the most sense, and you just want to do your own thing, you'd have to somehow make a function that's able to be aware of who's calling it, and once it figures that out, is able to then provide a different sleeper uptime function. And I had some ideas, some really crazy hacky ways to make that happen. It's unrealistic. It's ridiculous. So the best way is just to pass in your own sleep or uptime functions. And that's pretty much it for this biweekly meeting. Are there any questions, comments, or concerns about anything that I've gone over? Alrighty. All right, guys. I'll stay online. I have one more announcement to make offline.